This is Calculus 12, Chapter 7.5. We're going to be looking at applications of integrals, and we're going to concentrate on work. We're going to skip pressure and probabilities. Work is force times distance, and we're going to want to integrate with respect to distance. Force is mass times acceleration, so because we're integrating F, we need to make sure that we have a force. So check your units. So work can be defined as an integral, the limit, or just the integral f of x dx. And for our problems, as long as the force is in the same direction, we can sum up the separate pieces. Let's look at a simple problem first. A force of 40 newtons is needed to hold a spring stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done stretching another 3 centimeters? That means to 18 centimeters. Okay, and in physics we have Hooke's law, f of x equals kx, where k is the length beyond the natural length. So we have to do some subtraction here. So 15 minus 10 equals 5 centimeters. And I like to convert this into meters. And the reason for that is we can just use joules as our units. So F of 0.05, we have F equals kx. We need to calculate k first. So k times 0.05 equals 40 newtons. Okay, and we have k equals 40 newtons over 0.05 meters. And we have 800 newtons per meter. So now we can set up our integral. Work equals the integral from 0.05 to 0.08. Okay, so we're going from 15 to 18. So that's 0.05 to 0.08. And this is just k x squared over 2. Integrate from 0.05 to 0.08. And we substitute our k divided by 2. 800 divided by 2 is 400. And now we do 0.08 squared minus 0.05 squared. We get 400 times 0.0064 minus 0.0025. That gives us 1.56 joules. Let's look at a slightly harder problem. A heavy rope, 50 feet long, weighs half a pound per foot, hangs over a 100-foot high building. How much work is done pulling the rope to the top of the building? And how much work is done pulling half the rope up? So we need to think about this. Initially, x is 0, and at the end here, x is equal to 50. And x is the amount that we've pulled up. And the rope weighs at x is, we have half a pound per foot. Initially, we have all the rope, so that would be 50 minus x. And that's 50 minus 0. At the end, our length is 50, so 50 minus 50 is 0. So we're not pulling anything up at the end. So this is our linear interpolation. So our work is the integral from 0 to 50. And our weight is 1/2 50 minus x. And it's dx. This is our F. This is our D. And we have a half times 50 is 25. So that's 25x minus a half x. That's x squared over 2. And then we have to take 2 into the account for the exponent. So that's 0 to 50. And we have, plug 50 into here, we got 1250. Minus, we plug 50 into here, we got 2500 divided by 4. And we get 625 pound-feet. This is a multiply. So part B, we have the same antiderivative. So W equals 25x minus x squared over 4. We just have different limits of integration. And we're doing the first half, so that's 0 to 25. Plug 25 in there, we get 625. And we plug 25 into here, we get 625 over 4. And that gives us 468.75 pound-feet. Normal way of guessing is to say that lifting up half the rope is going to be half this value. However, that's not the case. The first half of the rope is much heavier because you're pulling up more rope. The second half of the rope is much lighter because you have less rope. So this is much more than half of this. Okay, let's look at a hard problem. We have a 2-kilogram bucket and we have a 20-meter rope that weighs 5 kilograms. And they're used to haul up water from a 20-meter deep well. The bucket can hold 20 kilograms of water. The bucket is being pulled up at a rate of half a meter per second. But water leaks out at a rate of 0.1 kilograms per second. How much work is done bringing the bucket up to the top? Okay, to calculate the bucket, the force isn't changing. F is constant. We don't need an integral. So it's just FD. So the force is 2, this is mass, times acceleration, and acceleration is 9.8 meters per second squared. This is just gravity. And we're hauling in a distance of 20 meters. We multiply that all out, and we get 392 joules. Now for the rope, that's exactly like what we just did here. So we have an integral from 0 to 20, because we're hauling at a distance of 20. Our gravity is 9.8. Now we need to figure out how much the rope weighs per meter. And that's just 5 kilograms over 20 meters. And we have the same linear interpolation. It's just the distance minus whatever the x value is, dx. Okay, so this is our force, and this is our distance. And we do the integration, we get 9.8 5x minus x squared over 8. And we're integrating from 0 to 20. This gives us 980 minus 3,920 over 8. And we get 490 joules. Let's pause for a moment and see if this makes sense. The bucket is 2 kilograms and it requires 392 joules. The rope is 5 kilograms, it requires 490 joules. So it's a little bit heavier, but the weight is changing as the rope is coming up, but it kind of makes sense that this is bigger than this. Okay, now dealing with water, the first problem is the water is leaking at a rate per time. The bucket is being pulled up at a rate per time. We want our force to be with respect to distance. We need our weight, our force, changing per distance. So it is leaking at, so our force, 0.1 kilogram per second, and we're dividing that by 0.5 meters per second. We can see that the per second cancels out, and we get 0.2 kilograms per meter. So now, if we multiply this by gravity, we get force changing over distance, and that's what we need. This is the hardest part to figure out conceptually. Okay, so we have 0 to 20. We still have gravity as our acceleration. Now we have 20 minus 0.2x. So our force is changing 0.2x per distance. This is our force. This is our distance. So if you understand this part, then it's pretty much like the rest of the problem. And we integrate this, we get 196x minus 1.96x over 2 squared. And it's 0 to 20. So we get 196 times 20 minus 0.98. 1.96 divided by 2 is 0.98. And x squared is 400. This gives us 3,528 joules. So most of the work is being done lifting the water. Total work, we sum it all up, 392 plus 490 plus 3528, and that gives us 4410 joules. Now for imperial problems, pounds is already a unit of force, it's not mass. We rarely use mass in imperial, but imperial mass, the units are slugs. If you're using pounds and feet, it's a slinch. If you're using pounds per inch, or snail. And again, these are very rarely used. And that completes this lesson.